Hi, everybody. Thanks for coming to talk today. My name is Clayton Davis. I'm the Director of Data Science at Modzy, and today we'll be talking about detecting drift in MLOps pipelines. So before we get started, we're going to talk a little bit about what drift is, because there's a whole bunch of terms that you'll hear people use: input drift, output drift, model drift, and a bunch of others. Drift itself is just kind of this umbrella term that we use to refer to when some sort of assumption that we made in our building of our machine learning model has been violated, and it's causing our machine learning model to misbehave in some way, right? Most often you'll hear it referred to as model drift, but I want to be really clear that that term, which implies that something has happened to the model, is a bit of a misnomer. The models haven't changed at all when you hear about drift. What's actually happened is essentially that one of three things have gone wrong. Either the outputs coming out of the model are no longer consistent with the outputs that were coming out during training. The input being added into the model is no longer consistent with the input that was added to the model during training. Or something's happened in the environment that the model is operating in, which is different than the environment when the model was being trained, right? Those three things, the outputs shifting, the inputs shifting, and the environment shifting, are essentially the root causes of the three different types of drift we're going to talk about today. And so we'll discuss them all as prediction drift, data drift, and concept drift. So let's talk a little bit about prediction drift, what it is, what it looks like, and kind of the way in which that you can understand it, right? So prediction drift is when that output assumption is violated, and when the data that you fed into your model at one time caused a certain number of classes to be output at the beginning that's no longer the same in the end. And so a good example of this is fraud detection. So when you're training a machine learning model, by definition, you need roughly the same number of examples of each class that you're training the model to identify. Okay? And so during the training of a fraud detection model, you would train the model with an equal number of cases that included fraud and cases that excluded fraud. And so the output during training would be roughly equivalent. If you had 1,000 cases of fraud, you'd have 1,000 cases of not fraud. But once that model is trained and you're happy with all of the metrics associated with it and its ability to predict fraud and not predict fraud, you're going to put that into a production system. And in the real world, the actual instances of fraud are negligibly small compared to the number of just general transactions dealt with by an organization on a day in and day out basis. And so your production distribution of your outputs are not going to look even for fraud and not fraud anymore. You're going to have a very few examples of the model attributing your input to fraud, and a whole lot of examples of your model not attributing the input to fraud, assuming the model is working effectively. And so that's prediction drift. Just the basic number of the basic number of output attributions for your different classes, in this case fraud and not fraud, has changed in some appreciable way in two different sections of time. We'll talk a little bit about how to actually identify when this has happened in a kind of a meaningful way here in a few slides. But first, we're going to talk a little bit about data drift, which is a violation of that second assumption about the input data not changing, and concept drift before we get to that. So in data drift, what's happened is that you've taken a model and you trained the model. Let's assume in our case that we've taken a model and we've trained it on these nice images that you see here on the left of this kind of blue car to identify when an image happens to be a car or happens to be, let's say, a motorcycle, right? So we trained the model, it's giving us good metrics, we're happy with it, but the way in which the neural net or the machine learning model in general sees the car is all through pixel values, right? And so if we take an image like the one that you see on the right, which we can also all tell is a car, right? It's a car of some sort, the door's open, the hatch is up, and we pass it through our model, right? There will be some value that comes out the end, because all machine learning models eventually give you a value. But the utility of that value for the second image is rather dubious, because the data itself that you are inputting into the model is significantly different than the type of data that was used to train the model, right? It's blockier, the resolution's lower. You can't really see or make out a lot of the features that you can see in the other image. And that difference, right, is what we refer to as data drift. It's when a model is presented data that is dissimilar to the data that it was used to train on, and the predictions that come out suffer as a result of that. Okay. And the final example of drift is concept drift. So I said there were three assumptions that we make that we build models that end up getting violated, and that's what causes drift. The first is that the outputs are different. The second is that the inputs are different. And the last one is that the environment around you has changed. Okay. So the example I like to give for concept drift is the prediction of creditworthiness pre and post a recession, right? 2008 is one that we can kind of all wrap our heads around, and so it makes a good example for this case. Leading up to 2008, decisions about creditworthiness and lending were, as they typically have been, made on assessments of your income, your assets, your debts, and to varying degrees, all of those things kind of combine together to make the decision to lend you money, right? Well, those models were built in a time before the recession when certain combinations of things like your debts and your assets and your income were predicting that you would be were predicting that you were a good bet for lending, right? And then in 2008, what happened is that those same values were no longer becoming good predictions of whether or not someone could borrow and whether or not someone could pay back a particular loan or a particular credit that was being extended to them. And so because of the other factors that were happening in the world, folks that had initially, say, very low debt or income to debt ratios before 2008 would be able to get a loan. Whereas after the crash in 2008, the threshold for, say, what your debt to income ratio had to be changed significantly as a predictive measure, right? The model didn't change, okay? The model itself would still predict in 2010 that the same people it predicted in 2007 should get a loan. But because the world around you changed and the people around you changed and the relationship between the good bets on the people who would pay back money changed, then you've experienced something called concept drift, right? And so the model, even though it never changed, and even though it was giving good predictions prior to 2008, because those values were no longer predictive of good bets and bad bets for the bank, it experiences concept drift, and it no longer works in 2010, where the relationship between how much income you have, how much debt you have changed have changed in some way that the predictions were no longer good and the models had to be retrained. So that's concept drift. And so why do we care, right? Why do we care about whether or not these assumptions are violated? The basic reason we care whether or not these assumptions are violated is that models are created in an instance to process data like the training data that's used to generate the initial model. So solutions that are affected by drift just aren't trustworthy. And so if organizations want to be able to use and leverage their AI investments on into the future, they need to be able to detect drift and they need to be able to mitigate it. And so we're going to take a look at a couple of different ways you can detect these three different types of drift, and then we'll talk a little bit about how you can actually mitigate these different drift forms. And so for detecting drift, you approach it differently for each of the three different drift types. For prediction drift, where, remember, we violated the assumption that the outputs should all kind of be proportional consistently throughout life. What we can do to detect that is basically just look at the outputs over two different time periods and compare them to see whether or not they're actually drifting. Usually we'll do that by calculating those distributions and then assigning some sort of statistical metric to them to decide whether or not we should be worried about the drift itself. For data drift, what we need to do is develop a way to look not just at the inputs that are being provided into the model, but the model's response to those inputs. We kind of call this the body language of the model. If you give a model an input and you evaluate not just the output that comes out, but also the way in which the model makes the decision for you, then it's possible for someone to kind of tell the difference between a model saying, yes, this image that you're showing me is a car, and a model that says, yeah, it kind of looks like a car. And those are the sorts of things that we need to be able to figure out when we're trying to detect data drift. And so we'll talk a little bit about that in a second. And finally, concept drift. Concept drift is completely beyond your control. Concept drift is happening not because of anything your model is doing, but because of things that are occurring outside of your model and just in the world and the environment that your model is operating in. If you really want to combat concept drift, what you're going to have to do is that you're going to have to establish a QA team that can periodically review the inputs and outputs of your model and say whether or not they are still valid or whether or not the environment and the vertical that you're working in has changed substantially since the creation of the model itself. Okay. So the way that we go about performing these detections for prediction drift, for example, is that we get 2 time periods. We'll say January through March, and the second we'll call August through September of, say, last year, right? And then we will take the data that was pushed through our model during those 2 independent time intervals through our machine learning model to generate the outputs. Once those outputs are generated, if there's only a couple of outputs, you can kind of eyeball it and look the way that you see on the screen here, the outputs that came out in our first interval versus the outputs that came out in our second interval. And you can say, hey, these are obviously different, right? This is the example taken earlier from the fraud case. Something seems weird here, right? But in most cases, that's not what you're going to be able to do. In most cases, the differences between your input and your output will be either very close, or one will be close and some of the other ones will be off, especially in situations where you have multiple classes being provided, being calculated, not necessarily just a binary classifier on one or the other. And so in the vast majority of cases, what you're going to want to do is be able to take that distribution and then run it through some sort of mathematical statistic that you can threshold and make decisions on taking action or not. So in the Modsy case, what we do is that we run 2 different time intervals through the models. We calculate those time intervals, and then we run through a chi-squareds test to establish a 99% confidence interval on whether or not those 2 distributions are the same. If a particular model doesn't necessarily meet the threshold for drifting, then you as an organization can sit back and be happy with the model that you're not experiencing prediction drift. If it does pass a particular threshold, then you're going to take some action that we'll talk about here in a couple more slides. If you're looking to detect data drift, you're going to do a thing that's similar to prediction drift with a couple of caveats. Again, you're going to go in and you're going to predict. You're going to have data sets from 2 different time periods. One of them is going to be from your production time that you can select at any point in which the model has been running. But the comparison timeline is always going to be the training data, right? Remember, data drift violates the assumption that the data that you're seeing in production is similar to the data that you saw during training. So what you're wanting to do is always make a comparison between the way the model is reacting to data that it saw during training versus the way that the model is reacting to the data that's being provided to it during production. And so you gather those 2 groups of data and you pass them through your machine learning model, right? You pass the training data through first. And what you do is you look at not the inputs and not the outputs, but what goes on in the middle of your machine learning model, okay? In the case of a neural network, all those middle layers, they happen to just be numbers. And so you can take those numbers and you can plot them. And so in this particular example, what we do is we take the training data, we push it through the model, and then we generate the plot on the right-hand side, where we can just assume that all of the points that resulted in an output of the neuron on the left are in red, and all of the training data that resulted in an output of the neuron on the right of the output model are sitting there in blue. For each case, when you're building up this model during training, those two cases are going to group together in kind of these intermediate representations that you have, regardless of how many layers there happen to be inside of the neural network. And so when you pass your production data through the network, if you're wanting to know whether or not your machine learning model happens to be confident in its answer, you're basically checking to see whether or not the network has seen something like this input before. And so as you take a particular input, you push it through the network. Let's say this green dot represents the production data you're pushing through. If that green dot shows up inside of this kind of red distribution or well inside of this blue distribution, you can be fairly confident that the machine learning model is going to predict an output correctly. You can be fairly certain that the data being presented to the model is similar to the data that was used to train the model. However, when you're looking at these intermediate representations, if you see that this green dot happens to be way up here in the corner, let's say the top left corner, what that's telling you is that the model has never seen anything like this before, right? By identifying where and how the model is treating your production data, and whether it's treating it the same by putting it in the same areas of the training data, you can assess whether the model is saying, yes, I am very confident in this answer, or yeah, I kind of think that the image you're providing me happens to be a car, right? And that's what you're trying to do in data drift, is really get a sense of the model's reaction and how the model is treating the data during the process, regardless of what the input and the outputs happen to be. And finally, concept drift. So I talked a little bit earlier about the fact that concept drift is something you have absolutely no control over. It's all about whether or not your environment happens to be training, or whether or not your environment happens to be changing. So if you think about the example we showed a second ago of the machine learning model that's capable of differentiating cars from motorcycles and trucks, and you present it with this image here of this blue vehicle on the top, what is more likely than not to happen is that the machine learning algorithm is going to classify it as either a car or a truck, one way or the other, mostly because of the wheels, the front, it's got seats, etc. But by technical definition, this is a Polaris slingshot, and it's actually a motorcycle. And so what's happened in this case is that the concept of what constitutes a car versus what constitutes a motorcycle has changed in the time between when the model was being built and what the model and the current day where the model is being used. Right? It had nothing to do with the actual model itself. But that's just sort of the world that the model has kind of like lived into, in a sense. If you're going to catch things like this, right, emergent behavior, or like earlier where the predictive values are no longer good at making the prediction that you want them to make, there is no set of math that you can do on the inputs, the outputs, or the machine learning models themselves. What you have to do is have a QA team who is constantly, or at least periodically, reviewing the data that's coming into your machine learning algorithms and the outputs they're putting out to make hand adjustments that you can then talk to the data science team about rectifying in your machine learning models themselves. And so that's really it on the three different types of drift, right? We have drifts that violate output assumptions, prediction drift, drift that violates input assumptions, data drift, and drifts that violate environmental assumptions, which was concept drift. In the case of the prediction drift, right, where the ratios of your prediction classes are changing in some sort of substantial way, it's not necessarily the end of the world. The thing that you need to do to rectify that situation is to go and manually evaluate the inputs and outputs for the new distribution in your latest time interval and see whether or not they're correct. There's nothing about an imbalance in the output that necessarily requires the model to be malfunctioning, right? And so if that model is functioning correctly after your evaluation, you simply rebaseline to whatever the new distribution happens to be. Okay. In the case of data drift, your production inputs just simply aren't similar to your training data. In those cases, you can't actually be certain of the trustworthiness of the output of the model. So you check the body language of the model, you see that the inputs are not making the model respond in the same way that they used to. And so now it's time to take the model and try to retrain it some. If there are only slight variations, you may be able to get away with some sort of fine-tuning, or a little bit of transfer learning, something along those lines. But if your production data is consistently different than the data that was used to train the model, it's time to think about retraining the model and just starting over, right? And finally, we've got concept drift, where the underlying assumption was that the environment was just simply always going to be the same, and that's changed, right? Whatever variables or good indicators that you used to have are no longer applicable. And the way that you get over that is simply to take a look at your model, use some human in the loop QA to periodically evaluate it. And when things have deviated, you need your data science team to help you make the assessment as to whether or not this model is savable and kind of transferable with a little bit more extra data, or whether it needs to be scrapped because it's simply no longer applicable to your situation. And so that's it. Those are the three different types of drift. That's how you detect them, and that's what you do about them. I'm going to be happy to sit around and take questions that anybody has, and dive deeper into the mathematics and the technical schemes behind detecting all these if anyone's interested.